Welcome to my YouTube channel, Usano-Goldie RL Marquez. This is Integral Calculus or Calculus 2, Basic Integration, Section 1.4, Exponential Formulas for Integration. In this lesson, I will be discussing indefinite integrals that can be handled by exponential formulas for integration. Exponential formulas for integration. Another basic integration formulas are exponential formulas for integration. Let u be a differentiable function of x. Then, the integral of a to the u du is equal to a to the u over ln a plus c, where a is greater than 0 but not equal to 1. The integral of e to the u du is equal to e to the u plus c, where e is approximately 2.71828. In the integral of a to the u du, a to the u is a power function not equal to a constant. A is the base, which is a positive constant different from 1. U is the exponent, which is a function other than a constant. And du is the differential of the exponent u. If all of these requirements are satisfied, then the integral of a to the u du is equal to a to the u over ln a plus c, where a is greater than 0 but not equal to 1. Example 1.3.1. Evaluate the integral of 2 to the 5x plus 3 dx. Solution. Given the integral of 2 to the 5x plus 3 dx, a here is equal to 2. The exponent 5x plus 3, let's try it to be u. Taking the differential of u, we have 5 dx. But there is a missing constant 5 for this to be du. Let's multiply dx by 5. Balance it outside by 1/5. Hence, this integral now takes the form of a to the u du. Therefore, this is equal to 1/5 times 2 to the u over ln a. But u is 5x plus 2 and a is 2. Simplifying, we get 2 to the 5x plus 2 over ln 32 plus c. Example 1.3.2. Evaluate the integral of pi to the 2x to the 5th times x to the 4th dx. Solution. Given the integral of pi to the 2x to the 5th times x to the 4th dx, a here is equal to pi. Its exponent to x to the 5th is its u. Taking its du, we have 10x to the 4th dx. But this x to the 4th dx is not the du. There is a constant factor that is missing, which is equal to 10. So let's supply this 10 for this to be du, but balancing it outside by 1 over 10. So this integral now takes the form of integral of a to the u du. So the integral is equal to pi to the x to the 5th over ln pi times 1 over 10 plus c. Simplifying, we have pi to the x to the 5th over 10 ln pi plus c. Example 1.3.3. Evaluate the integral of 10 to the cosine 3 theta times sine 3 theta d theta. Solution. Given the integral of 10 to the cosine 3 theta times sine 3 theta d theta, we identify that a is equal to 10. Let's take cosine 3 theta to be its u. Taking the du, we get negative 3 sine 3 theta d theta. This sine 3 theta d theta is not exactly the du. We need a constant factor negative 3. Let's correct the differential by multiplying by negative 3 and balancing it outside by negative 1/3. This now takes the form of integral of a to the u du. Hence, we have in negative 1/3 times, so the integral is equal to 10 cosine 3 theta over ln 10 plus c. Simplifying, we have negative 10 to the cosine 3 theta over 3 ln 10 plus c. Example 1.3.4. Evaluate the integral of e to the tangent 2y secant squared y dy. Solution. Given the integral of e to the tangent 2y secant squared 2y dy, let's take tangent 2y to be its u. Du is equal to 2 secant squared 2y dy. But this secant squared 2y dy is not exactly the du. So there is a missing constant factor 2. Let's correct the differential by multiplying by 2, balancing outside by 1/2. So this is now equal to the integral of e to the u du times 1/2. We have 1/2 e to the u plus c. Example 1.3.5. Evaluate the integral of 3 square root of 3y to the 4th plus 2 y cubed dy over square root of 3y to the 4th plus 2. Solution. First, let us express this integral in the form of integral of a to the u du. So getting integral of 3 is to the square root of 3y to the 4th plus 2 times y cubed dy over square root of 3y to the 4th plus 2. So our a here is 3. U is equal to square root of 3y to the 4th plus 2. Its du is equal to 12y cubed dy over 2 square root of 3y to the 4th plus 2. So simplifying, we get 6y cubed dy over square root of 3y to the 4th plus 2. So here, this is not exactly the du. So we need to multiply it by 6 and then balance it outside by 1 over 6. This is now in the form of integral of a to the u du. A to the u du. So this is equal to 1 over 6 times 3 to the square root of 3y to the 4th plus 2. This is u over ln a. A is 3 plus c. Simplifying, we have 3 to the square root of 3y to the 4th plus 2 over 6 ln 3 plus c. Example 1.3.6. Evaluate the integral of x to the 6 e to the log of 1 minus x to the 7 dx over 1 minus x to the 7. Solution. First, let us express the given integral in the form of integral of e to the u du, getting e to the logarithm of 1 minus x to the 7 times x to the 6 dx over 1 minus x to the 7. In this integral, u here is log of 1 minus x to the 7. Let's see if this is its differential. Taking the differential of u, we have negative 7 x to the 6 dx over 1 minus x to the 7 ln 10. But this x to the 6 dx over 1 minus x to the 7 is not exactly the du. we need a constant factor -7 in the numerator and ln 10 in the denominator. So let's correct the differential of u. So we have to multiply here inside the integral by -7 over ln 10. Outside the integral, we multiply it by its reciprocal, that is negative ln 10 over 7. This integral now takes the form of integral of e to the u du. So getting negative ln 10 over 7 times e to the u, but e to the u is equal to e to the log of 1 minus x to the 7, then plus c. Example 1.3.7. Evaluate the integral of e to the tangent inverse of y squared times y dy over 1 plus y to the fourth multiplied to pi to the tangent inverse of y squared. Solution. Given this integral, let us express it in the form of integral of e to the u du. Here there are two possible e to the u. One is e to the tangent inverse of y squared, and then the other one is pi tangent inverse of y squared. One in the numerator, one in the denominator. But notice that they have common exponents. So let us express it in the form of e over pi raised to tangent inverse of y squared times y dy over 1 plus y to the fourth. A here is equal to e over pi. Let's take tangent inverse of y squared as its u. Taking its du, we have 2y dy over 1 plus y to the fourth. But this is not exactly its du. So we need a constant factor too. So let's complete that with the du by multiplying it by 2, but balancing outside by 1/2. So this now takes the form of a to the u du. So we have 1/2 times a to the u over ln a plus c. But a here is e over pi and u is tangent inverse y squared. Simplifying, we get e over pi raised to tangent inverse of y squared over 2 ln of e over pi plus c. Example 1.3.8. Evaluate the integral of e to the 3 cosecant inverse of 5 ln x dx over x ln x square root of 25 ln squared x minus 1. Solution. First, let us express this integral in the form of integral of e to the u du. So we have integral of e to the 3 cosecant inverse of 5 ln x times dx over x ln x square root of 25 ln squared x minus 1. U here is equal to 3 cosecant inverse of 5 ln x. Let's check its du if this is really the du. So getting the differential of u, we get 3 times negative 5 over x dx all over 5 ln x square root of 25 ln squared x minus 1. Simplifying, 5 is cancelled, so we have negative 3 dx over x ln x is square root of 25 ln squared x minus 1. But this differential is not exactly the du. So there is a constant factor missing, which is negative 3. So let's apply that negative 3 for this to be du, balanced outside by negative 1/3. So this integral now takes the form of integral of e to the u du. Hence, we have negative 1/3 e to the u plus c, but u is 3 cosecant inverse of 5 ln x. Example 1.3.9. Evaluate the integral of e to the cotangent inverse of 3w plus cotangent inverse of 3w dw all over 1 plus 9w squared. Solution. First, let us express this integral in the form of integral of e to the u du. We split this into two factors, e to the cotangent of inverse of 3w and e to the cotangent inverse of 3w times dw over 1 plus 9w squared. This is equal to integral of e to the cotangent inverse of 3w times e to the cotangent inverse of 3w dw over 1 plus 9w squared. Let's take e to the cotangent inverse of 3w as u. Its du is e to the cotangent inverse of 3w times derivative of this inverse cotangent 3w is negative 3 dw over 1 plus 9w squared. Let us apply simple u substitution. Solving for e to the cotangent inverse of 3w dw over 1 plus 9w squared, we have negative du over 3. So this integral now is equal to integral of e to the u, and this differential is negative d over 3. Factoring out negative 1/3 outside the integral, we have integral of e to the u du times negative 1/3. So this now in the form of integral of e to the u du, and it is equal to e to the u plus c. So times 1/3 here, so we get negative 1/3 e to the u plus c. But what is u? E to the cotangent inverse of 3w. So getting negative 1/3 e to the cotangent inverse of 3w plus c. That's all for now. So these are some exercises that you can have for practice. Evaluate the given indefinite integral. So there are 8 numbers. Thank you for watching. Please don't forget to subscribe to my YouTube channel, Usano-Goldie RL Marquez.